All right, welcome. And let's see here, we're going to do polar coordinates now. So I know most, if not all of you, have seen polar coordinates, so this will probably be a review and won't go nearly in depth as probably what you did in STEM or pre-calc, but gets us ready for the calculus of polar, which is what we're going to do on Thursday. Anyway, just a reminder, rectangular coordinates, that's XY, that's what we're used to. It describes a horizontal and vertical movement and tells you how to find the position of something. Polar coordinates, sometimes referred to as trig coordinates, these are in the form of r, theta. R is for radius because it represents the which circle you're on with a radius of r from, and it's centered at the origin, and then theta is the angle around the circle that you're at. So, um, what's interesting, I think, I don't know. Anyway, I think math is cool, so what can I say? But a point only has one pair of rectangular coordinates, but there's actually an infinite number of polar coordinates to describe a location. So let's take a look. If we take a look at point A below, point A is at the point. Oh my goodness, it's not at 3, 0 though, is it? It is at the point 0, 3. Um, and that's in rectangular. So only one pair of numbers that describe it in rectangular form. When you're doing polar, you could say it's on the circle of radius 3 and it's at the angle pi over 2. So we have a circle of radius 3, that's a horrible circle, but 3 units away from the origin, and it's gone around the circle pi over 2 radians. Or we could say that it's gone around the circle negative 3 pi over 2 radians. So maybe we use this pair to describe it. Or what's crazy is we can have a negative r. We could say we're at negative pi over 2 radians, so on this array right here. But then when we talk about a negative radius, rather than going in this direction, we go the opposite direction 3 units and still wind up at the same point. Or we could be at the ray negative 7 pi over 2. 1, 2, 3, 4, 5, 6, 7. That would put us on this ray again, but again, negative 3 radius goes in the opposite direction right there. And you can see we could play this game forever and we could have an infinite pair of polar coordinates to represent the same point. So anyway, there's that. Just to kind of test yourself, try plotting these points. And actually, let me back up in case you haven't seen a polar graph before, but I'm sure you have. But a polar graph, rather than being in a grid form, it looks like concentric circles. So we still call this the origin, and we have concentric circles drawn around it, and then we have the angles drawn. And so, for instance, if we do the first point together, the point 5, pi over 4, well, we don't have a ray to represent pi over 4, but we know that it would go right here. And we want to go 5 units away from the origin, or on the circle with radius of 5. 1, 2, 3, 4, 5, right there. And that is point A. So see if you can plot the other points. Pause the video and just take a look, and then we'll look at it real quick together. All right, so for B, we're going to go to the ray 3 pi over 4. Again, this one is not drawn on this particular graph, but we know 3 pi over 4 would go about here. And so I want to be negative 3 units. So I want to go to the opposite direction. So I'm actually going to go this way instead, and I'm going to go on the circle with the radius 3. And there's point B. Negative 7 pi over 6. I'm looking at point C now. Negative 7 pi over 6 would be the same thing as positive 5 pi over 6. So I want to be on this ray here. but we're going to go 2 units away from the origin or in the circle with a radius 2. So it's going to end up going right there. And there's point C. And then point D has a radius of 0. We can put whatever angle we want here. If we're at a radius of 0, we are automatically at the origin. So that point would go right there. Okay, so there's plotting in polar. If you want to convert back and forth, we've seen this before. You probably saw this back when you were doing the unit circle. So we still have these formulas here. X is our cosine theta, Y is our sine theta. You can remember which one's which because of alphabetical order. X comes before Y, C comes before S. The radius is really, it makes a right triangle with the X and the Y coordinate. So this is the Pythagorean theorem right here. And then here, tan theta equals y over x. Notice I am not saying theta is tan inverse y over x. We're going to use this to help us solve it, but it's not always equal to this because remember that tan inverse has a specific range of negative pi over 2 to pi over 2. It will only give you answers in quadrants 1 and 4. So if you're in quadrants 2 or 3, you have to add pi, but you have to think about that. You'll see what I mean. So let's take a look. Okay, let's convert the following from rectangular to polar. So pretty straightforward. R is pretty straightforward. R is the square root of x squared plus y squared. So R is the square root of 2 squared plus 5 squared, which that would be 4 plus 25. That'd be the square root of 29. And then tan theta is y over x. So tan theta is 5 over 2. Now let's just think about this really quickly. The 0.25, this is in quadrant 1, which is in the range of tan inverse. So we don't have to make any modifications. That's our answer right there. R theta. And if you needed to, you could type this on a calculator and get an approximation for that theta. But that's the exact answer. Okay, let's try the next one. 3, negative 4. 3, negative 4 is in quadrant 4, which is in the range of tan inverse. So I won't have to make any modifications here. I'm going to use those same formulas for r and theta. So r is the square root of 3 squared plus negative 4 squared. This is just going to be a Pythagorean triple. This is 5. Tan theta is y over x, which is negative 4 over 3. So theta is tan inverse of negative 4 over 3. So the point is r theta. And there we go. All right. When you have something like this, 0, negative 4, if you're on one of the axes, just think about it. 0, negative 4, that's going to be down here, 4 units away. It's 4 units away, so the radius is 4, and the angle that it's on is 3 pi over 2, and you're done. You could go through these, use these same formulas, but so much easier to just do that. And then for part D, we have this guy right here. If you think about it, it's actually one of the ones we know. Now you can use the formulas and you'll get to the same place, but if we draw this out real quick, and this, I mean, which way's faster? I don't know. It's good practice though. 2 root 3, 2, well, let me just label it like this. So 2 root 3, this is 2. I don't know if this looks at all familiar. Hmm. Have we seen those numbers before? It's 30, 60, 90 triangle. If we go ahead and work it out, can you figure out what the hypotenuse would be? And can you figure out, I mean, don't trust my picture being drawn to scale. Maybe it is, maybe it isn't. Can you figure out what the angle is? So if we were to use our formulas, r equals 2 root 3 squared plus 2 squared in a square root. 2 root 3 squared is 12. 2 squared is 4. That's 16. So r is 4. This is in the ratio of 1 root 3, 2. I don't know if that rings a bell. And then if we do tan theta is y over x. Tan theta is 1 over root 3, or root 3 over 3. So theta is pi over 6. So it's our 30, 60, 90 triangle. If you happen to spot it, it can be a little faster than going through all of this stuff, but 4 pi over 6. And then this one we can get an exact answer for theta and not have it in terms of tan inverse. Now I do have one more here. This guy right here is in quadrant 3. So when we do theta, we just have to add pi. So let's take a look and see why this works. Okay, so r is x squared plus y squared in a square root. That'll be 16 plus 36, which is 52, which simplifies to 2 root 13. Tan theta is y over x, which will be positive, and actually I can even reduce it to positive 3 halves. So theta is, well, it's not tan inverse of 3 halves. If I leave it like that, this is in quadrant 1. It's positive, the ratio is positive. The output for tan inverse is only in 1 and 4. Tangent is positive in quadrant 1. I know this is in quadrant 1. I want to get over here to quadrant 3, so I'm going to add pi to do it, to make sure that I'm in quadrant 3. So just watch out for that. Make sure that you're in the right quadrant. And there's my answer. So that's converting from a rectangular to polar. The good news is, if we're going from polar to rectangular, it's so straightforward because we have very easy formulas that we use. So sometimes you can think of the picture, and again, it's one of those, like, these are all, except for part D, these are all angles that we can either use a triangle or the axes for. Um, it's probably whatever's easiest for you is what's easiest. I'm going to use formulas for the first one. So x is r cosine theta. So x is 3 cosine negative pi over 6. Cosine of negative pi over 6 is root 3 over 2. So there's my x. Y is r sine theta. And r is 3. The sine of negative pi over 6 is going to be negative 1/2. So my points are 3 root 3 over 2 and negative 3 halves. That's my x and y coordinate. Now negative 5 pi over 2. Pi over 2 is a quadrantal angle. It's one of the axes. So pi over 2 would be here, but it's a negative radius, so I'm going to go in the opposite direction down there. So the point is 0, -5. There we go. Same thing here. Although this one, the radius is 0, I'm automatically at the origin. I don't even have to think about that one anymore. There's my answer there. And then for part D, I'll have to use a calculator here or just leave it in terms of sine and cosine. So the x-coordinate is r cosine theta and r sine theta. Because cosine is an even function, we know cosine of a negative angle is cosine of the positive angle. Sine is an odd function, so sine of a negative angle is negative sine of the positive angle. So I can write it like this, make it a little nicer, or just type it in on the calculator and see what the answer is. So there's that. So that's converting polar to rectangular, a lot more straightforward because you just use r sine theta, r cosine theta. You can speed things up a little bit if you have some easy angles to work with. All right, now this is kind of prepping us for what we're going to be doing, but think about this. Describe the pink, yellow, and green regions using inequalities with r and theta. Okay, let's look at the pink. We'll do the pink one together. So the pink ones. So I'm starting with a radius of 0, going out to a radius of 2, and every point in the pink region is between those two radii. So pink is 0, is less than or equal to r, is less than or equal to 2. And then as far as theta goes, everything in the pink region starts at 0 and goes to pi over 3, from 0 to pi over 3. So 0, less than or equal to theta, less than or equal to pi over 3. So now that you see what they're looking for, see if you can do the yellow and the green regions, and then we'll check in. Go ahead and pause the video and try it out. Okay, hopefully you did. The yellow part starts at a radius 2, goes to 4 all the way. So 0, oops, not 0, oh my goodness, I just said it. 2 is less than or equal to r is less than or equal to 4. And then theta is going from pi over 3 to 2 pi over 3. All right, and the green. R is going, 0 is that? 1, 2, 3. It's going between 3 and 4 all the way, radius 3 and 4. So, doing it again. 3 is less than r is less than 4. And then theta is, be careful here. So we're down here at 5 pi over 3, and then we're ending here at pi over 6. So you may be tempted to say 5 pi over 3 to pi over 6. However, this would be incorrect because this is gibberish. This value is larger than this value, but the inequalities say that this value would be less than. We can't start at a larger value and increase to a smaller value. Can't be done. So you may say, well, okay, easy fix. We'll swap them. We'll take pi over 6 and put it here, and 5 pi over 3 and put it there. Now we're going from the smaller value to the bigger value. You can't do that either because that says you're starting at pi over 6 and increasing until you get to 5 pi over 3. And that is not where the green part is shaded. So there's multiple ways of doing this, but the most straightforward way would be to start at a negative angle here. So whoops, let's call angle down there at 5 pi over 3, it is coterminal to negative pi over 3. So now we can start down here and go in the positive direction and increase to pi over 6, and that will take care of all of the green, because pi over 3 is coterminal to negative pi over 3. And so that would have to be the inequality that we use. Okay, so there's that. Now, let's practice converting equations. So here's an equation right here. Xy equals 1. We know it would just be a hyperbola, but let's go ahead and convert it to polar form. Now, there's different ways you can go about this, especially when you're doing something like part B, where you're going polar to rectangular form. But for this way, I think it's easiest, just go ahead and use the fact that x is r cosine theta and y is r sine theta. And then if we can, let's solve for r, at least get the r kind of by itself, like all the r's on one side. Anyway, we have r squared cosine theta sine theta equals 1. So if I divide by cosine theta sine theta, I get r squared is secant theta cosecant theta. And that's good. We'll leave it like that. And there we go. Okay, let's take a look at part B. Now, there's a couple different ways, like I said, to approach this. You're going to wind up getting to the same point. We want to be able to use our formulas that r squared, or r equals the square root of x squared plus y squared. And we do have an r here. I don't really want a square root on my answer if I can avoid it. Let's see. I'm going to go ahead, and one way we can do this, and I'll show you another way, which is almost the same. We know that x is r cosine theta, so that means that cosine theta would be x over r. I can replace cosine theta with x over r. And then I can multiply both sides by r and get r squared equals 2ar. 2ax, I mean, whoops. Now, another way I could have done this to get to the same exact place is if I just multiply both sides by r in the beginning, I would get r squared equals 2ar cosine theta. And then we know that r cosine theta is x. You can see we get to the same exact thing. And it really took the same amount of steps. So just different ways. Now, of course, we still have r, so we have to take care of that. But now we know that r squared is x squared plus y squared. And then it becomes one of those things like, how do you know when you're done? I mean, if you can solve for y, you definitely want to do that. We could solve for y, but hopefully you also recognize this is an equation of a circle, just not centered at the origin. So I'm going to go ahead and I'm going to subtract 2ax from both sides. And I'm setting it up for completing the square. Completing the square, take half of b, so half of negative 2a would be negative a. Square it, you get a squared. Whatever you do to one side, you do to the other. This factors into x minus a squared plus y squared equals a squared. And now we know it's a circle. Radius is a, center is a 0. So it's a little nicer to put it in that form. So there's converting. Now, some graphs that are good to know. If we just have the equation r equals a constant, then that describes a set of points that are on the circle with a radius r. So that is a circle centered at the origin with a radius r. And then we just did this one. If you have this equation, it turns out that um, it does have a radius of a, and the center is at a0. Radius a, center is at a0. It's the exact same equation we did. And then if we, instead of having cosine, if you had sine, that's still a radius a, but now your center is at 0a. So cosine, if you think about where a0 is, it's right here. It goes like this. So the equation with cosine is along the x-axis. The equation with sine, 0a, that would be up here. If it's sine, it's along the y-axis. And then anything with theta equals a constant, that is just a line with a slope of m. And so there you go. Those are just some nice ones to know. These especially are going to come into play um, next with the next unit or in the next section that we do. Okay, our last problem we're going to do. Let's see how we graph something like this. Now it's not exactly what we had above. You may be thinking, oh, it's just a circle, but it's 3 theta, not just theta. So this is not going to be a circle. So what does it do? Now one way you can do this is you can just make an XY table and plot points. But another way you can do it is you can graph a corresponding equation in rectangular form to help you easily get a bunch of points to put on here. So if I was going to graph this, y equals 2 cosine 3 theta, this has an amplitude of 2 and a period of 2 pi over b, which is 2 pi over 3. So that means it's going to finish a cycle in 2 pi over 3. So I'm going to go 1, 2, 3, 4 over, and I'm going to label this as 2 pi over 3. So that means halfway is pi over 3, and half of that is pi over 6. I'm going to go ahead and just label all these points now. So we got 1 pi over 6, 2 pi over 6. This would be 3 pi over 6, which is pi over 2. 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. I like to go up to 2 pi. You may not need it all, and you'll see what I mean by that in a second, but going up to at least 2 pi lets you see what's happening. Okay, so this is a cosine graph. So cosine will start up at the amplitude, go to 0, go back down, back to 0, up, back to 0, down, back to 0, up, and so on. So it's going to do something like this. And now I have not only a bunch of points that I can use, but I also have what's happening in the graph. So what I mean by that is this. First, I'm just going to label all the points that are mins and maxes or intercepts. I like to see what's going on. let's say IJKLM. I like to see the order of the points. So remember that my y is really the radius. So this y value of 2 really means I'm on the circle with a radius of 2, but I'm at an angle of 0. So I am 1, 2, I'm right here. That is where point A is. Now point B has a y coordinate of 0, which means it has a radius of 0. All these points along the x-axis is where I'm at the origin. So there's a lot of points at the origin. I'm not going to label all the letters, but I just know after A, I'm going to go back to the origin. And then I go to point C. Point C is at the angle pi over 3, but it's got a negative radius. So here is the angle pi over 3, but I'm going to go this way because it's a negative 2, so I'm going to be right there. And that's where point C is. And then D would take me back to the origin. E is at 2 pi over 3 with a radius of 2, so it's right up there. F takes me back to the origin. G is at pi, except it's down here with a negative radius, so I'm going to go in the opposite direction. G is actually going to take me back to A. It looks like I'm going to repeat now. So it looks like I only needed to go halfway to figure it out. Let's just spot check and see. H would take me back to the origin. I would be at 4 pi over 3. And 4 pi over 3 is along here with, yeah, it does look like I'm repeating myself now. So it looks like I'm going to go from A to the origin, to C, back to the origin, to E, back to the origin, to, and no, I'm obviously not doing just this, because the question is, how am I getting from A back to the origin? Do I go straight? Do I go along a circle? What am I doing? I'm not really going straight or along a circle, but to go from A to B, my radius is positive the entire way, but my radius decreases. So I am at a radius of 2. While I'm going around the circle, I am also getting closer to the origin. So I'm doing something like this, and then I go to point C, and I'll turn around, and I'll go to point E, and I'll turn around, and I'll go back to point A, and I'm just going to trace it. And I end up making this thing over and over and over again. And so here's the graph. And it only took 0 to pi to complete the rose. This is a rose with 3 petals is what we call it. So there you go. That gives you a way of graphing without just making an XY table. So here's some things to start with. Your homework is actually pretty straightforward. So if you finish early, just be good and work on something quietly. All right. That's it. Have fun, and I'll see you guys on Thursday. Bye.